So I wanted to take inventory on where was I at, and that is solving this differential equation numerically along with some game dev shit. So let's take a few notes. We'll have a few magic numbers, initial conditions at 0, and this is our advancement through time constants, and again some magic numbers. So if I were to take some notes on these, what's happening here is we're doing a numerical Euler's method on this system of differential equations. So the very first thing you notice is what happens when you press left and right. Never mind up and down. You notice this B over H, something that was written in the computational domain, and we wish to take it back to the real domain, and we notice that if we ignore this divided by H and put a fucking B here, let's set this B to 0, just like we set DL to 0, and then set this B to 0 here. And we'll call this B0 as like a fucking initial. And here it has this. And let's see. Okay, that was just a fucking order of magnitude error. But what I did is I brought this the fuck. So when you press left or right, instead of, just, doing the game dev way of incrementing the acceleration or the force, it turns out it's actually the driving force of the differential equation in terms of t, wherever it is that you press the left or right arrow key, the differential equation is driven by this function. And that's nice. I mean, to me, that just cleans up the code a bit, if anything. So the next thing I want to do is analyze this system in phase space. And what we're going to do is introduce a new layer to the screen. As such. And every time we update the pendulum visual, we will draw plot across the entire screen, which is the angle theta on the x-axis versus its derivative, that is d theta over dt, which of course we're computing numerically. And this is called this is the so-called phase space plot. So let's just write it down. On the x-axis we have a 1. Let's center it around pi over like such. Okay. So already we see the so-called phase space of the pendulum. So let's just do one maneuver, and that is somewhere near the bottom we'll lengthen it. which causes it to oscillate at a small angle, meaning that in this kind of resolution, this is a circle, because if you look back, in the small angle case, theta is some constant times a cosine. Therefore, the derivative of theta, which would be the y-axis here, is some function of sine with some exotic fucking amplitude. But anyways, so let's do let's not touch the left or right arrow keys here, and let's just shorten the length and speed ourselves up. And here we are. We went one over, but nevertheless we are tracing a so-called elliptical function in phase space. So it's no longer a circle or an oval or an ellipse as you would expect. And let's say, as we're swinging, we kind of speed up. And now we are in this I don't know what you call this, unbounded region in phase space. Tracing out this curve, the sort of eyelash to the eye, and let's just use the driver to reverse its anyways, so this is our basically complete game dev phase space trajectories mapping of our pendulum. And what was I saying? So when you press the fucking left or right arrow keys, you're introducing a driving function, f of t, to the differential equation. And here we've just assumed that as we're analyzing this dl over dt is 0, so we get no damping. And then because a differential equation is just a suggestion for an integration, we're able to use this fucking suggestive notation for the integrator to only apply this constant b at a certain time interval, but I mean, let's do the neurotic thing. Let's plot a few trajectories in phase space very cleanly by using the left and right arrow keys, which is our driving function. Now let's give it, yeah, another circle oval. And of course, 2 is never enough, so let's do 3. Fuck it. 5 for neuroticism. Okay, so then let's go. There we go. Let's do some eyelashes because we're effectively doing our makeup. Let's do one here. Fuck. Okay. Uh, okay, let's do this eyelash. And let's do one more. Okay. That's fine. So let's do kind of neurotic demonstration of the concept of damping. That is when you reduce this termin, no, fuck this. This termin right here, and we'll do this by increasing the length at appropriate times. And what should happen is we should be tracing a spiral in phase space. And if you're following along, that is precisely what we're doing, is we're tracing a spiral from the outer edges of this phase space by lengthening the string and thus affecting the damping constant in the right way. And this is your fucking... And there you go. And having said all that, if one were to further explore the branchial space of this equation, one would find a particular case where, you know, over the course of this phase space, we've pressed the keyboard fucking hundreds of times, maybe however many, which doesn't really correspond to a singular pulse train, the driving pulse train. So let's assume we press the keyboard infinitely many times in eternity. Let's conduct a thought experiment, that is, setting this so t sub something is the array of times we operate the keyboard. Uh, 1 second. So as I was saying, t sub something is the point in time where the user presses a key on the keyboard. But as a thought experiment, you know, looking at the periodic nature of this phase space, let's presume that the user, the omniscient presence, only presses the key at integer multiples of a period that is periodic. So this driving factor becomes a fucking let's say periodic function. F of t becomes periodic. And what the fuck does that mean? So a lot of you will say, oh shit, this is just the kicked harmonic oscillator used to introduce chaos theory. But because this is periodic, and the solution, the fucking homoerotic solution to this equation is also a periodic function, whether you use the small angle approximation and get periodic sinusoid, or whether you fucking get the elliptical function of the first kind. But what you're doing here is you're mixing two periods out of sync for a kind of spirograph effect. That is, this system obeys a certain natural frequency determined by this magic number GL, but you're driving it with a periodic function whose frequency is slightly out of sync. And if this anyways, what the fuck? Okay, let's just do the following. So let's take these magic numbers and do the following. For initial conditions, let's start with 0. So in this sketch, let's remove this fucking... Okay. So we have a basic phase space. And pi over 2, what the fuck is pi over 2? Let's give it a 2. 3. You know, pi over 2 is that kind of the point where the function becomes from circular to allegedly elliptical. Anyways, so here is our complete phase space minus the what I wanted to say basically is that when you're employing this kind of Euler's method, transforming one set of coordinates to another using, you know, this kind of fucking step size in a slope field, what you can do is you can really fuck it up by increasing this magic h or step size into something idiotic. In particular, let's say just fucking get rid of it altogether, and here just get rid of it all the fuck together. And let's say I'll call this some fucking 1.2, and look what you have. You have Absolute fucking madness. So let's go 1.3, 1.4, 1.5. Okay. So if you're following along, we explored the branchial space of the simple pendulum as such into a kind of spiderweb of chaos in the phase space domain.